into a little bit more meaty subjects. Okay, so for deep learning, as we talked about, there are you have basically an input and output component to that, and a bunch of hidden layers. And as we talked about, deep learning is most of the research is currently targeted at deep learning because it's the most effective learning method there is out there in terms of the set of problems it can address. There are, however, limits in terms of one of the challenges with deep learning systems versus analytic methods is that with analytic methods, a lot of times people have the kind of think, actually I should say, they think they are more comfortable because they understand the features better and they understand how the AI or how the model has managed to, because it's an analytic method, they think it's more deterministic. The reality is that that's not the case. I think explainability is a big unknown in AI. There's a whole branch of AI called XAI, which is about explainability, but I'm not an optimist in that area because I think that when you ask a human being, like how is it that you know that this is a dog or a cat? I don't think any of us can tell you. It's like, what are the set of unique features that make this a dog? Well, if we knew that, then we could actually write a program for that. It's we don't know. It's like how our brain processes information. We have so the visual cortex has a very complex way of putting together features to assemble a understanding that this is a dog or a cat. And but if you ask us what those things are, we're probably going to get down to the neuron level to understand really how is it that we tell that it's a dog or a cat or something like that. And if you try and say, well, it's got 4 legs, well, there are a lot of 4-legged animals. If you talk about when you talk about genetic differences, then a machine can obviously tell the difference then, because that's a very easy way, and you probably don't even need a machine learning model to do that. So I would say that this is, So I don't think XAI will necessarily yield results. What I do believe is that better empirical methods are needed to determine the validity of a model. And by empirical methods, it means treat it as a black box, but make sure you've got good confirmation values around it, which means that you need to understand things like F1 score. It could be things like you have the traditional measures, sensitivity, specificity. You can look at validation accuracy, look at the accuracy over the general population. You probably do a Bayesian analysis. All these things are things you can do to increase the confidence, but what you're doing is you're looking at the high level overview, like the measures of the system, rather than actually trying to understand how the system works. And I would say that that's not really, like if somebody asked me, I'd say XAI and explainable AI is nothing that I would feel confident that we'll ever have an answer to that. At least not an answer that's meaningful. Because in theory, with convolutional neural networks, you can essentially look at each of the layers and you can see what set of features were picked by that layer. But those features are meaningless. If for a human eye, it doesn't mean anything. It's like it doesn't look like anything that's useful. And I don't think that the human brain, when in terms of how we break down an image, I don't think that there's any element that we can easily describe to people. So anyway, that's my bias there. There are many different types of neural networks for different kinds of problems, as we talked about. These are different, kind of hard to see, but I can kind of at a very high level describe some of the more common ones that you're likely to run into. So the first thing is kind of deep feed forward networks. This is the most common type of deep learning model. It is used mostly for classification types of problems. So deep feed forward network, what that means is you could have like 2 directions. You can have basically a bidirectional neural network. You can also have like one that essentially is actually over here. So feed-forward network is right there. So essentially, you've got the data propagating there. You've got like a back propagation to train the model and adjust the weights. So that's one way. Convolutional neural networks are basically, we talked a bit about that, used for image classification and machine vision problems. It's mostly about automated feature generation for the different images. Recurrent neural networks are largely used for analyzing sequences like words in a sentence, and that's they're used everywhere. So you'll see a lot of neural networks work that way. So recurrent neural networks work that way. So what they're good at is they basically relate previous information or previous data to the next set of data, and that's what they're good for. Long short-term memory is an LSTM network. So basically, a type of RNNs that are good for determining long sequences. So RNNs are typically for shorter sequences, but LSTMs are really long sequences. Autoencoders, it's an unsupervised network that essentially takes an input and returns the input. So it's a model that you're essentially training to generate itself. So which means that autoencoders can be used so that if you have partial information, your AI can then reconstruct the original information, original data. So that's one way. You've got deep belief networks. So deep belief networks, an example of that would be GANs. So these would be, well, it's basically, so what you can do is you can generate, so it learns certain patterns and then generates networks based on those, generates data based on the learned patterns, and GANs are basically kind of the same thing. So this complicated picture is what a neural network looks like. So on one hand, let's say you have the input side here and the output here. So what you notice is that, of course, these are all connected. So you've got this node is connected to these next three nodes. So each of these connections have weights associated with them. The weights indicate how strong that connection is or how weak that connection is. So in traditional neural network, so when you think about an organic neural network, that sort of corresponds roughly to the idea of the strength of a synapse or how strong a synapse between two neurons are. So synapse is kind of like the connection point between two neurons. And so as you learn things, then essentially what you're doing is you're changing how the strength of different synapses, and that's how you formulate ideas or concepts or whatever. So this is kind of the same thing here. So if you have an input, let's say x1, I'll now have to go to the board. Okay, so let's say you have an input vector, which could be, let's say, two features. And these two features are represented by x0 and x1. Okay, so all that is basically you have two features. It could be, like if you talk about the bug case, it could be duration and name of the engineer. So there's some way to represent the name of the engineer, which is probably a number like between 0 and 10 or something like that. You've got 10 engineers. And then duration could be just a number like that. So if you have the next layer, which is a set of neurons, so I'm going to have like 3 neurons there, then what you have is you have the connections, like, so this is like W01, W02, and W03. So those connections, and those are the strengths associated with that. So the way to think about it is you take the input and you multiply it by each of these weights and then add them. And so you have sort of, let's put it, so y 0 prime is equal to x naught times W01 plus, sorry, let me just take it back. So let me take this back again. So you've got x1, which is basically then connected to these nodes as well, because I need to do this. So you've got like w, let me just make this 0 based. And then you've got x1, which is w10, w11, and then w12. Right? So that would be kind of how your overall neural network works. So then the question then becomes, so what are the values here? So what are the outputs? So imagine that these are distinct outputs. So here, what you have is this node 1, let's call it just node 1, and we'll say this is y1. So y1 is basically the sum of this times the weight w00, right? Equals x0, w00. But there's also an x1 component, so it has to be the second component, but now it's w10, so it'll be plus x1, w10. So what I'm doing there is it's a mixture of these two values and multiplied by the weights associated with that. So then if I go here, let's put 0, y1, in this case now, can anyone tell me what that would be? Just what the equation for that would be? W01. Yeah. Plus x1, w11. Yeah. Correct. And then y2 equals so x0, yeah, w. X1, sorry. Right. So that would be kind of like what the output values are. So, okay, great. I have all these different values. What do I do with them? Well, that's where the activation function comes in. So one of the things about neurons is when a signal propagates, it hits a synapse, and so you've got like neuron A, you have a signal that kind of propagates there, and then a signal that kind of continues on. So when the signal goes between one neuron and another, it basically crosses some sort of a threshold, and that threshold, if you don't hit that threshold, then no signal actually goes between the two synapses, and so there's no strong connection there. If there is a strong connection between if the signal does go through because you exceed the threshold, then a signal does go through and that strengthens that synapse. Every time a signal goes through that, that strengthens that synapse. So there's the idea of a threshold. So the output of each of these things is a raw value. And what you want to do is see whether you have hit a certain threshold. And so the threshold could be as simple as if it's below a certain value. So one very simple threshold function could be if x is less than some t, then you have some value t or like I don't know v1, and then if it's greater than or equal to t, then it's v2. So that could be an example of a threshold function. Typically, this would be 0 and 1. This is like when this is going back in time when the first set of neural networks were created. They were just simply like a 0 and 1 base, and it was a simple threshold function that when it was below a certain value, then it would be 0. When it was above a certain value, it would be 1. Since then, there are many other threshold functions that kind of give you tell you what the final output is. And ultimately, what these are called are activation functions. So activation functions, the parallel with biology is that you're essentially activating a neuron by sending a signal across. So what you end up doing is the true output, which is y0 prime, is equal to the activation value with y0 as your input. And so that's the actual output of the entire layer. And then you got y1 prime equals activation function of y1, y2 prime. So this is the output of this layer, and then they feed into the next layer, and these become the inputs into the next layer, and so on and so on. So that's, neural networks are easy. So it's pretty straightforward. So don't be too frightened. But that's basically what's going on. So in the same picture, W00, W010, you multiply that by this vertical, and that becomes y prime. Or I've flipped over the notation, but basically that's, I'm essentially multiplying this by a matrix. So the matrix in this case is simply your input vector, which is x0, x1. And what I'm doing is I have a matrix, so you'll notice that it's W00, W10. So W00, W10. And when you multiply that, you get Y0 there. So it's a simple matrix multiplication. So in some sense, what you can argue is that all neural networks are a bunch of matrix multiplications followed by an activation function. So, there are different types of activation functions. So you see kind of logistic, which is kind of like a simple S curve. You have tan H, which the differences between that and logistic is that it goes from -1 to 1. And then, so then you've got soft plus, which is unbounded at the top, so it starts from 0, goes through that. And then you've got ReLU, which is kind of almost a little bit like soft plus, except that it's got a discontinuity at 0. But otherwise, the others are constant function, are continuous functions. But those are, and so very often you see ReLU being used with convolutional neural networks. Soft plus is very often an activation function that you use, that you see from many different types of problems there. You see logistic and logistic functions very often as a kind of an output when you're trying to bound it as a value between 0 and 1.